You wait at the nominal steady state. You wait until everything upstream is quiet, so you don't see any major disturbances, and do a small step change up. Wait until you reach the new steady state. Get the response curve, fit k tau and d. Bring it back down to the original steady state. Small step change down. Same thing. There's another reason why you need to make a small step change as possible, because there's a reason why you operate normally at the nominal steady state. That's the best place to operate, right? So you lose performance when you step away from the nominal steady state. And so also from that point of view, we want as small step change as we can. Okay? And also, from a mathematical point of view, small step changes means that nonlinear terms that I'm neglecting are indeed small.
There's a big difference between the Ks.
Yes. If you want, for your own benefit, if you have the time, go ahead in your own time, make step change 0.1 up and down. You find that the Ks are much, much closer. And as you decrease the step change, it will not be exactly at this average, but you see this average is closer to what you're getting than. Although, to be honest with you, one thing that I have not investigated is if a geometric average might be better. That I'm not sure. Yes?
How do you know what's the right step size that you should get?
That's what I'm saying. As small as you can, while you still get your data that is not masked by noise. So it depends on how noisy your system is. Okay? The less the noise, the smaller the step changes you can make from a practical point of view. So you have to look at your actual data. Okay, so the grand result of this is that for the CSTR gain, we found that GU equals minus 61 over 44s plus 1 e to the minus 6s. Robert, somebody? All right. Now, I want you to make an important correction. I'll go to the class website in a second to point out what the next thing we're doing. It's time now to tune our first feedback controller. And it's a classical method called the Cohen-Kuhn method. And this is log and chug for first order plus time delay. It's only for first order plus time delay. And what type of controllers do we have? A little bit now of introduction, and we're going to be spending most of the time today on that topic after we finish this exercise. But what type, when we talk about feedback control, what do we mean? Feedback control means now that the control valve that changes the flow rate of the coolant, and therefore indirectly the flow rate of the coolant, is going to be some function of the error, and the error is y set point minus y measured. This is the desired value. This is what I'm actually measuring. Okay? We discussed when we did the CSTR gain that the simplest thing to do is to take corrective action in proportion to the error. What's the corrective action? Corrective action is manipulated input minus nominal value. That's the corrective action. And proportional control is standing for proportional. Simply takes the corrective action proportional to the error. We let the manipulated input change in proportion, so to keep the corrective action proportional to the error. Clear, everyone? This has got big disadvantage. It doesn't eliminate steady state offset. It does not return, with the exception of a special case, it does not return the system back to the set point if a disturbance comes in and doesn't return to its nominal value.
What is KC?
KC is a parameter, it's called the controller gain. So tuning, if I have a proportional controller, controller design means selecting the value for KC. But KC normally doesn't do the job. Just proportional control normally doesn't do the job. And I alluded to this in the past, that what does the job, what eliminates steady state offset, what guarantees that eventually my measured output will go to the set point, that the error, that's supposed to be an R. Eventually the error becomes 0 if we add a term proportional to the integral of the error. So the next step in complexity is the PI control. And that takes the corrective action. In addition to having a term that's proportional to the error, that's a good idea, but it doesn't do the job by itself. We add a term proportional to the integral of the error. And this is a definite integral, so here is a dummy variable. You can use any variable you want inside it. So now we have two parameters. This is the controller gain. And this is called the integral time constant. So designing a PI controller means determining two parameters, Kc and tau I.
KC's controller
Gain.
controller change.
Controller gain.
Gain. Every time.
Gain.
Every time.
Hmm?
Every time is gain. Positive.
It's called controller gain. No, it doesn't mean it's positive.
Okay, that's
Can
what
be
I was
negative.
Okay.
Kc must always have the same sign as K if the process is open loop stable. Okay, that's why I'm very severe if you mess up this sign. Because if you mess up the sign of K, you mess up the sign of Kc. And that's what brings disaster. So the one thing you must make absolutely sure, never mess up the sign of Kc. Now, classical control has a third mode, adding one more term, and that term is proportional to the derivative of the error. And that leads to the PID control.
What does PI stand for?
Proportional integral. So P control for proportional, PI control for proportional integral. These are standard abbreviations. Mika.
What's next to the tau?
Which tau?
The one in the front.
Here? Integral time constant.
Oh, no, but I mean like it's tau I or what?
Tau sub I. Yeah.
Yeah, sorry, I can't, it's a little hard.
Okay, sorry for that. And you also have PID control. And I will actually add the prefix ideal, which is not implementable. This has another term that is proportional to the derivative of the error. The derivative of the error, what is derivative? It's the slope, right? That gives us predictive action. And has the potential of significantly improving controller performance. However, if you have noisy measurements, the derivative will be just the outcome of the noise. It would be a disaster. As a matter of fact, even from a mathematical point of view, from a practical point of view, you cannot implement what is called the ideal PID control. It's always implemented with something called a low-pass filter. A filter is something that smooths the noise. If this is your measurement, and with low-pass filter, what happens is it becomes, this is with low-pass filter. Hold on, I just wrote what I want to write at the end. And always in industrial controllers, you'll never see the ideal PID controller, and unfortunately, many books only list the ideal PID controller. But the one that is implemented is something with a low-pass filter. And so let me write what is the ideal PID controller. That's the corrective action. We have what we have in the PI. I have to raise this. And then we have another term. This is called the derivative time constant. Derivative of the But that is never implemented like that. It's implemented with the filter that I mentioned before. But then we have a third parameter. So in this case, designing a controller is finding values for Kc, the controller gain, tau I, the integral time constant, and tau d, the derivative time constant. Now, if you go to your notes, and I want to bring it up because there's an error that I would like you to correct. Let's jot the note down. I don't want you to be tuning a controller with my notes and mess it up because of that. So if you go to the class website, what we're doing, go to APC6. We started on APC6. Wait. Here we go. Focus. Okay, here we go. You can see here what I was talking about. The P controller, the PI controller, the ideal PID controller, and okay, we'll talk about that after the break. But the first controller tuning method is the Cohen-Kuhl method, and that's plug and chug. And right here is the Cohen-Kuhl method. Notice everything is now plug and chug. Big correction here. Tau I for PID is missing a D in front of it. It should be D times this, like there's a D here, there should have been a D here. So, let's tune our CSTR gate controller. Because I don't have a filter coded in, putting derivative action would be disastrous. I can show you in a minute how bad it would be with derivative action. If we put just proportional, we'll see that we'll have steady state also. But let's tune both a P and a PI control. Okay? So this is my GU, and let's write down what the tuning would be for a proportional controller only and for a proportional integral controller. Actually, let me just do it on Excel. Okay? So, let me start Excel. Is everybody with me? I didn't go too fast with it, did I? I know I went fast at the end of one. But I was going to do it slow today, so that's why but it was okay for me. All right. So let me put here the parameters. Maybe first of all, so that we can all see it. I'll make it really big, 16. So here's the K we have, here's the tau we have, and here's the T. So the K was minus 61. The tau was 44. Oh. The tau was 44, and the D was 6. So, for P control, there's only one parameter to tune. And that's Kc. So the Kc for P control, let me, so we can see this. You can see the equation, and notice Kc always has 1 over K. Automatically has the same sign as K. So if you mess up the sign of K, you mess up the sign of Kc. I've said it about 5 times, but it's that important. So 1 over K, oh, equals. What does it equals?
Should we name them first?
Equals 1 over K times.
You need to create from selection on that.
Hmm?
You need to create from selection to make them together.
We're not going to be doing any copying, so I don't need to name it. That is that what you're asking.
I don't know, just maybe usually like create from selection so it references K in the equation instead of referencing.
Well, okay, we can name them. All right, that's not all right. If you name them and click, then it puts the name. Since I'm not going to be copying, that's why I wasn't going to name, but it's okay. It doesn't matter. Makes it more readable. So, expand it to see the name on it. Create from selection, left column. So I named it. Okay, let's now continue. So Kc equals 1 divided by K times tau divided by, I don't put any parentheses, then it's from left to right if you don't put any parentheses. Multiplication and division have the same priority, so it does things from left to right. So divided by D times, now I need the parentheses, 1 plus D divided by 3 divided by tau. So minus 0.13 is the controller gain I would be using if I used only proportional. Let's also do the tuning for PI. So that will have a Kc and a tau I. 2 parameters.
Tau y?
Questions? Just type whatever way, if you want to put parentheses, whatever way you feel comfortable, type it. Felix.
Can you leave some space between KC and PI?
Sure.
Thank you.